vad är klockan?
Okay. En minut.
Jag sätter mig där nere. Du får vinka åt mig om det börjar bli panik så kommer jag springa ut. Ctrl L för att maximera programmet. Du får lämna orkesterlådan ute tills du börjar prata.
Hello, everybody. Day one is almost over, but we have one last talk left. This talk is entitled Runtime Kernel Patching for OS 10. The speaker is Torbjørn Lufterud. I believe I pronounced that close to correct. He is filling in for the speaker who could not make it. He actually has the swine flu and is in the hospital. But this speaker is the co-author, the replacement speaker is the co-author of the FRAC article that is the basis for this talk. So I will turn it over to him.
Thank you
very much. Give him a warm welcome. Thank you.
All right. Thank you very much. As you've already heard, I'm not Bosse, but I'll do some PowerPoint karaoke here with you and try to use these slides to kind of fill, and you have to excuse me if I'm unable to fill in the gaps in his slides. And I'm also going to tell you right away that I will not be able to run the demos that he has prepared. So I'm obviously not Bosse. My name is Torbjørn Lufterud, and I work for a Swedish company called Cybercom. I also have somewhat of a more healthy fetish for breaking stuff. But we're here to talk about Mac OS X and runtime kernel patching. The first thing we're going to do is talk a little bit about what a rootkit actually is. Then we're going to talk about the usual way of doing kernel patching in the Unix environment. And then we're going to talk about some of the specific parts about using Mac OS X. Then we have a short proof of concept. And then we're going to talk about detection and have a Q&A. So, what is a rootkit? Well, a rootkit is something that you use once you've actually been able to hack into a system or gain access to a system. It is not an exploit. It is not a Trojan horse. It's all about stealth. It's all about hiding your activities and hiding your presence in a system. The main focus is often about hiding files and hiding processes. For instance, your backdoor or your sniffer that is running. You can hide sockets, and in many cases, you use it to hide or obscure your presence in an already exploited or hacked system. There are 2 or perhaps 3 different types of rootkits. We have the standard userland rootkits, which was popular in the old days. They replace binaries in the file system, usually processes involved with displaying files, processes, network sockets, and these types of utilities. With the introduction of advanced tools like Tripwire, which can be used to monitor system integrity, these these tools are not efficient anymore. It's very easy to detect. It's very easy to remove, and if you, especially since there were a number of standardized toolkits that can use for this, it's very easy to detect these kind of rootkits. So, for this reason, we move into the kernel and we write kernel rootkits. These rootkits do basically the same thing. They hide the presence of a backdoor or of a sniffer or some kind of other dubious process. There have been a number of really good rootkits for the Linux environment and also for Mac OS X and for Solaris. There's also a number of rootkits for Windows. We would like to mention Phalanx by Rebel, Swedish guy, Suckit, of course, Knark by Creed, also a Swedish guy, and Weapon X by Nemo, which was the first rootkit that I looked at for Mac OS X, which also inspired me to investigate this further. These rootkits use different technologies. For instance, Phalanx and Suckit both do memory patching using /devkmem on the Linux platform, while Knark and I believe Weapon X also are kernel modules. And this talk is basically about memory patching. So, I'm just going to change. So, what about the Mac OS X kernels? Mac OS X is a Unix-based operating system. It supports, it is built up by different modules. At the lowest layer, there's the Mach kernel. And on top of that, we have we have the BSD sublayer. These different components handle different kind of problems or different part of the operating system. The BSD layer handles networking, processes, and the POSIX subsystem, and the Mach kernel or the Mach layer handle things like processes and kernel threads, interrupts, memory management, and scheduling. And the interesting part for us here is memory management. The kernel, or the Mac OS X kernel, supports loadable modules. And if you're interested in how to create kernel modules or kernel module-based rootkits, I would really like to recommend our FRAC article on the subject. But this is not why we're here. We talk about direct memory patching for the Mac OS X kernel. We want to subvert the kernel without using loadable kernel modules. And we want to hook system calls and change their behavior in order to stay hidden. We can also manipulate other type of structures in the kernel, but we'll look into that later. So, whenever you have a process that is running in user space that wants to invoke something inside the kernel, it will call on a function. And what we want to do is that we want to intercept these function calls and change the output of the function. If you have a program that calls, I think in this example, it's function A calls function B, we want to intercept that function call and intercept our evil hook in between. I wouldn't agree on using the word evil, I would say alternative, but we'll just have to go along, it's his slides. In order to do this, we have to introduce our own code into kernel space. So the first thing that we have to do is allocate memory in the kernel. This is somewhat of a tricky part in most operating systems, especially if we are doing this in Linux, for instance. It's very tricky to allocate kernel space. Then we want to introduce our alternative code into the kernel and replace the system call that is called by the user function with our own code so that we can intercept that call, change the output or input if that's the case, and return the result to the user. Profit. If we want to do this in the Linux operating system that doesn't have the mock kernel API that we're going to look into later, we're going to do this in a somewhat cumbersome way. The first thing we have to do is try to allocate some kernel space. In Linux, when we need to read and write to kernel memory, we use the pseudo device. Okay, perhaps I should move back a bit. We use the pseudo device /dev kmem. This pseudo device allows us to read and write directly to kernel memory. In recent versions, they might have limited this capability, but in concept, it's the same thing. It allows us to read and write to kernel memory, but we are unable to allocate memory. So how are we going to allocate memory? What we do is that we find a syscall that is not very often used, such as set host name, for instance, in this example. This is a syscall that will be very seldomly used. And we choose one that is not used often to avoid race conditions. Then we remap that syscall into the kmalloc function, which is used to allocate kernel memory. And then we invoke that function. When we invoke that function, what is going to happen is that instead of calling set hostname, the kernel is going to invoke kmalloc and allocate some memory for us. Once we get the pointer back to that memory, we can restore the original function and restore the system to the previous state, knowing that we now have a piece of kernel memory that has been properly allocated and can be used. There are alternative methods to doing this, in that we can find certain parts of the kernel space that we know is unused or that we know is very unlikely to be used for something else, and that we can use to introduce our own code. But the popular way of doing this is to hook an unpopular function in kernel space. Now, in Mac OS X, on the other hand, we have a few other tools at our hands. Instead of reading and writing to /dev kmem, we have mock IPI kernel functions that we can use. VM read, fairly simple, read and write, reading to virtual memory. VM write to virtual memory, and VM allocate. Now, this is the thing that makes this special. It's a very, very useful function. So the first thing we have to talk about when we talk about VM read, write, and allocate is that we need a port into the kernel. The Mac OS X mock kernel uses something called tasks, threads, and ports. A task is basically a virtual representation of an execution environment. A task can contain threads. So in many cases, it's a process, like you start Netscape or Bash or something. That would be a task. It has its own address space, just as any other, as normal processes does, but it can contain threads. Each thread is, as in any other operating system, has its own execution identity, and it has its own scheduling. For each of these, we have something called a port. And this is not my main area of expertise, so I'm going to have a bit of a trouble explaining in detail how this actually works. But we use the ports to communicate between different parts of the operating system. And the interesting thing here for us is that we have a port so that we can communicate with the kernel. These ports are used in inter-process communication between different parts of the operating system and also between different processes. But in order to communicate with the kernel, we need to access its port. And the kernel always has 0 as its port. In this very small example, how many of you can actually read this? Well, a few of you in the front rows at least. The interesting part here, I wish I had a... Does someone have a laser pointer or something I can borrow? Well, I'm just going to stand here and jump. Let's do it like this. Okay, so task for PID, Mac task self, and here 0. This is so that we can get a read and write pointer to the port in the kernel. So it's fairly simple. Ask for task for PID for 0, and then we do VM read on that port. That's as easy as it is. Of course, this requires root access, as I'm sure all of you understand by now. But once we gain root access, we can use these commands to read and write to kernel memory. This has some very interesting implications. If we can read and write to kernel memory, we can change basically everything. Mac OS X, for instance, has something called security levels, which is basically a mirror of the BSD concept of security levels, whether or not you are allowed to, for instance, load kernel modules. So if you want to, you can disable the possibility of loading kernel modules in order to protect yourself from kernel modules-based rootkits. But since we can read and write to kernel memory, we can flip that bit for the security level so that we can reintroduce the possibility of loading kernel modules. Very, very good to know. Writing to kernel memory is basically the same thing. We use task for PID on 0, get the port, and then we use VM write on that port. Fairly simple. And of course, the really interesting one for us is VM allocate. This allows us to allocate memory inside a different process. And in this case, we want to allocate memory in the process used for the kernel. This allows us to use a very, very easy way to introduce new code into the kernel. So, what is it that we really want to change in the kernel? Well, in this example, which I believe is the... okay, it wasn't an example, it was just a struct. Sorry. The thing we want to change in the kernel is the sys entry. So I think I'm going to... There was a really nice slide explaining this one. Yeah. So I'm going to start with this slide. Whenever a user process invokes a function in the kernel, we use something called the sysentry table. So if we, for instance, want to hide a process, or if we want to hide a file, let's take the file example because it's very easy. If we want to hide a file, we have a backdoor that is an executable, and perhaps we have a sniffer that generates a log, and we want to hide these artifacts of our intrusion. We want to hide these files. We want to modify the function used by the kernel to display files to the user. So when the user types the command ls, or uses the finder, for instance, to enter a directory and browse the contents of a directory, he will invoke the function getDirEntries, which is basically a small kernel function that looks to the file and looks to the file tree and returns a list of files in that directory. In our case, we would like to modify that list of files, and we do this by intercepting the function getDirEntries, let the original function run, take the data back, parses through the data, find the entries that we want to remove these entries from the data, and then return the end result to the user. So in this case, the original syscall, which in this case here is open, the original execution flow would be that it looks up the syscall open in the syscall entry table, and then invokes that function. In our case, we want to divert this call flow. We want to change the sysentry struct table so that it points to our own function, and when we actually run this function, we're going to invoke the original open function if we want to, or we can just end it there or say the file does not exist, or in the case of open, we could, for instance, open a different file. Opening a different file comes in handy if we want to replace a file in the file system. Let's say that we want to, as an example, we could say that we want to switch out the SSH binary. We want to have an SSH binary that logs usernames and passwords used by users in the system. but we don't want Tripwire, the integrity monitoring software, to actually detect that we have changed the binary. So we're going to modify the open call so that if you open the file in execution mode, it opens our new binary. But if you open it in read mode, as Tripwire, for instance, would do, you give it the original file. And then you hide the new file using, by changing the characteristics of getDir entries. So in this case, what we would do is that we would subvert the sysentry table, call our new function, and in that function, we would call the original open call and change the output, or change the path. But the sysentry table just basically contains a list of system call functions and their address in kernel space. So let's go back here. So the syscall entry table contains a large list of function pointers. Each function pointer contains a number of properties, for instance, the number of arguments, flags, the implementation function, which is pointed to the actual function. The problem for us here is that we need to find it where it is in kernel space. Landon Fuller actually developed a really nice way of doing this for kernel extensions. When Mac OS X was at, I think it was like version 10.3, Nemo released his WeaponX kernel rootkit. This rootkit basically mirrored how Knark worked for the Linux platform, in that it just simply replaced certain functions in the sysentry tables, and Apple responded to this by removing that table from the exported symbols of the kernel. That means that we cannot simply reference the sysentry table in our code when we develop using Xcode, for instance. So if we develop something using Xcode, if we reference the sysentry table, as its name, just sysent, it will simply say unknown. It doesn't know what it is and how to use it. But there is something else that we can use, and that is called something the nsysent. And that is basically a variable containing the number of available syscalls. This variable just happens to be stored next to the sysentry table in the kernel space. So Landon Fuller developed this very, very short routine that basically finds the nsys variable and then returns that value plus 32. So if you're on the x86 platform, it's plus 32 for unknown reason, probably something that has to do with compiler alignment. And if you're on your PowerPC platform, it's just next to it. So this way we can find the sysentry table even though it's not exported from the kernel. Now, doing this in user space is basically the same thing. We don't have the kernel extension where we can just reference an object like nsysent, but we have access to the actual kernel. It's in /mark kernel. And it contains the nsysent symbol, which can be resolved just as we do inside a kernel extension. And as I said before, it's just 32 bytes away. I think there was a beautiful example, but there wasn't. So the kernel image is just a normal binary, or Mach-O binary, containing two architectures, i3xx and PPC. And Bosse actually developed this really nice little library that you can use to resolve kernel functions. It's called libs2a. And in this small example here, it basically just says resolve the nsysent function and add 4 if it's on a PowerPC, or add 28 if it's on add an additional 28 if it's on a PowerPC platform, on the x86 platform. So we've actually located the sysentry table. We can read, we can write, and we can allocate space. What are we going to do? Brings us back to this slide, which I basically already talked about. But what we're going to do in the case of open or get dirent, for instance, is that we want to subvert the normal execution flow of this function, and we want to replace it. Now, if we do this using a kernel extension, we can compile our own C code and load it into the kernel, and the compiler and the loader will assemble and link our own our code. If we do this using raw reads and writes to the kernel, it will not assemble. It will assemble it, but it will not link it for us. So we would have to have assembly code that we basically introduce, or binary code that we introduce into the kernel. But the concepts are virtually the same. So, Bosse developed this really nice proof of concept rootkit that uses these techniques. I'm afraid that I will not be able to run his really fancy demos, but it uses this technique to hook the read and I think it's get dirent and something else. You can look it up. He has it available on the web, and you can try it out. So I'm just going to skip the demo part here. So I'm going to talk a bit about rootkit detection, because this is also interesting. Can we actually detect if we've been infected? Is there some way for us to know if we've been infected? Well, in the case of modifying the actual syscall entry tables, yes, there is. We can compare it to the original syscall entry table in the mock binary. If we, for instance, use, we can use nm or we can use utool, whichever suits you the best, to look up the syscall entry table. And in this case, so this example is a bit complex, but we know that the number of syscall entries is difficult. 427, which in hex is 0x1ab. Then we can search for this value in the kernel using the utool, which basically just outputs in a decimal. And then we can grep for this value. And as you've seen in this example, we found it here. And guess what? 32 bytes later is the syscall entry table. So we can read the kernel into a buffer. We can find the sys entry table using the nsysm symbol, and we can compare to the original content of the drive. So he has this really nice function that reads in the kernel and actually searches does a binary search, finds the nsysm table, the nsysm variable, and then the sys entry table in order for us to use that as a reference. And since we're running all of this in user space, it's really simple. So we have this function that reads up the mock kernel from disk. Then we can just do task for PID, open up the memory for the kernel, and just read using bmread and compare these tables to make sure that they're actually the same. There are, of course, other ways of subverting syscall functions than to actually change the sys entry tables. But if we have a rootkit that actually does change the sys entry table, and this could be changed using either the kernel extensions or this method, the method of actually finding or detecting the change is the same. So we can do these searches from user space very simply using these tools. I can mention that other types or other ways of subverting a syscall would to be, for instance, to go into the All right, let's try again. All right, now you can hear me. Yeah, so a different way of actually subverting the flow of a syscall is to subvert the interrupt handler. So whenever a function or a user function want to invoke a kernel syscall, it actually goes through the interrupt handler and the interrupt handler table. So we can actually modify or change that as well. But the interesting thing here is that the method of actually opening the kernel from hard drive and comparing it to the actual kernel in memory is valid even in that case, because we can do the same thing. We can compare what we are expecting on disk to what we are expecting to see in memory. And it applies to basically all kernel functions or kernel methods that are static. Of course, it doesn't apply to something that is dynamically allocated. But for basically everything else that might be interesting, it virtually applies. I'm sorry I can't run a demo here, but I can mention a few other ways of doing basically the same thing. If we want to detect that someone has subverted something in the kernel, we can look for artifacts of that change that has appeared. For instance, we could compare the number of open sockets that the system has available to the list of sockets that we are actually able to bind. So if a backdoor has binded the port 999 and it has been hidden, we could try to bind all of these ports. And when we run into a port that is not listed, but that we are unable to bind, that would be the indication that there is something wrong. So, if you want to delve into this deeper, there's a number of really interesting sources out there. We actually have Abusing Mach on Mac OS X by Nemo. It's what actually the thing that got me interested in this topic. We have Mac OS X Wars, X New Hope also by Nemo in FRAC64. And of course, we have me and Busse's article in the latest FRAC 66. There's the Mac Hacker's Handbook, and also the slides and some of the code should be available on the website. Unfortunately, the website is currently down. Otherwise, I might have been able to run the demos. Sorry. But I'm sure as soon as Busse gets better, he will be able to provide you with the demo code as well. And we would like to thank Hack.se, Rebel, Nemo, and the people at Basic, and of course the people at Cybercom for making this possible. That's it. Do you have any questions? I see someone has a question. Thanks.
Hi, thanks. I just wanted to ask, do you know how much of this is relevant to the iPhone as well?
It's relevant to... interesting question. How much of this is actually relevant to the iPhone? I would say almost all of it is relevant to the iPhone. The iPhone has a few peculiar features with regards to signed binaries and stuff like that, which might make things a little bit difficult. But once you actually root and you start to write into kernel memory, most of these things are basically gone. But you would actually have to do it, my guess is, on a jailbroken phone. But it should be applicable if we disregard the things about the signed binaries. More questions?
Hi, my name is Michi Leenaas from NLS Foundation. So I came here because I thought you'd be doing something similar to a project that we fund called Ksplice that does real-time kernel updates, but to patch kernel holes. Have you ever tried patching kernel holes that that you found in so to see if you could use this in a benevolent way?
So the question was basically, is there any good ways to use this technology, or can you use it for good? And the answer, of course, yes. If you, for instance, find a security hole in one of in a kernel function, the example that I have for you is for the Linux kernel. I believe it was membreak or something like that, which was a kernel function that had a serious fault in it. I used a Linux kernel module to just hook that function, do the sanity checking on it, and that's just pass the control back to the original function. And of course, you can do this in Mac OS X as well, using both kernel extensions and these memory patching techniques. It all kind of depends on what it is you're trying to do. But in many cases, if you know what the fault is, or if you know exactly what it is you want to change, you can do it in runtime. And the good thing is, of course, that you don't have to reboot after applying your own security fix in this case. So the answer to the question is yes, you can use it for good as well. More questions? All right, thank you very much. Bosse won't be at the bar, but I will. So if you have any further questions, please let me know. Thank you very much.